is going to talk about prior free profit maximization.
Okay, so this is joint work with my student Tak Nguyen, who's over there, and Yuval Paris from Microsoft Research. I'm going to skip the outline. So I'm talking about the same setting that Jason was talking about earlier, I think, mostly, which is single parameter profit maximization. You have an auctioneer who's offering or allocating a good or service. You have a set of n agents. Agent I has value VI for receiving this service. And there are constraints on which subsets of agents can simultaneously be served. So, for example, single item auction, you could only serve one person. Digital goods auctions, you can serve anyone. This multiple markets, exclusive markets, this is an example where you have multiple markets, but you're only allowed to sell, let's say, in one of them. Or the single-minded combinatorial auctions. So those are just some examples. And an auction in this setting is going to take as input a bid vector and choose as output one of the feasible subsets, which will be specified by an allocation vector xi, the probability of allocating to the player with value vi, and a price. So that's what the auction does. The agents, knowing the auction design, are assumed to bid to maximize their own utility, which is their value for what they receive minus whatever they pay. And our goal is to design truthful auctions that maximize the auctioneer profit. And I think everyone in this room knows what truthful means. I'm not going to repeat that. Let me just remind you that in single parameter settings, we actually understand what truthfulness means pretty well. There's a well-known characterization due to Myerson, I guess originally, that a mechanism is truthful in expectation if and only if the allocation rule, once you fix the set of bids for everyone else, the allocation rule for player I is monotone non-decreasing. And once you specify the allocation rule, the payments are determined. And for deterministic mechanisms, this boils down to, given the bids by everyone else, there's some threshold bid above which that player wins, and that'll be the price they pay. Okay, so a common approach in economics is the Bayesian approach, where we assume that players' values are drawn from known prior distributions. And as we've heard already several times, there's a beautiful general result that gives the optimal Bayesian auction in any single parameter environment when the player's values are drawn independently. And as we've also already heard, there are some downsides to assuming priors. It may not be convenient, reasonable, or even possible. And we don't really know how sensitive the results are to errors in the prior. So one of the approaches we've tended to take in our community is to try to do worst case prior-free profit maximization. And this, when it's possible to get very positive results, this is like the best thing you could possibly hope for. It's extremely robust. You're not assuming anything. Even on the worst input, you do well. Okay, so that would be great to get positive results in that sense. Okay, so how do we design truthful auctions that are approximately optimal in worst case? Well, again, as Jason already said, there is no absolute best truthful auction. So what we've been led to doing is kind of use a competitive analysis type framework. And the way that works is we define a profit benchmark, which takes a vector of valuations or bids by the player and spits out a target profit that we would hope to achieve. Okay? And this is sort of saying, what should we shoot for each possible input? And then we try to design an auction that is always close to this profit benchmark for all possible inputs. So the worst case ratio is going to be called the competitive ratio of the auction. Actually, it doesn't matter here. But, and we'd like to basically get very close to whatever our profit benchmark is. So So then the question becomes, given a profit benchmark, design a truthful auction that gets as close as possible to it in the worst case. And this sort of begs the question of what the profit benchmark should be. And this was a major part of Jason's talk as well, but it's not very clear how to choose a profit benchmark. So, for example, in the early work on digital goods auctions, the first thing you might think of is trying to extract the full surplus, the best you could possibly hope for if you didn't have to extract the players' values, and you quickly realize that this is too strong a benchmark. No auction can be constant competitive to this. You can be log-n competitive to this, but when you're log-n competitive, you don't necessarily distinguish between a good auction and a bad auction. And the second try, which basically worked, was to set your profit benchmark to be the best fixed price profit. So meaning you fix a price, you sell to all bidders who are willing to accept that price, namely all bidders whose value is above that price, and you choose the price to maximize your profit. And there are old papers that show that there are auctions that have constant competitive ratio relative to this, as long as there's no dominant bidder, and there are lower bounds, and it's all very nice. But it wasn't really clear after this paper, or these papers, whatever, to how to extend this benchmark definition, or why even necessarily it might have been the right definition in this setting. And but it just seemed to work here, and so that sort of raised the question of how to choose the benchmark. So Jason suggested a benchmark earlier today, but I'm a couple years behind Jason, so I'm actually working with a suggestion he made a couple years ago. And I will call this the Heartline Rough Garden Framework. This was proposed in their paper on money burning. And they basically proposed a way to think about the benchmark question that was really tied together the Bayesian optimal mechanism design with prior free optimal mechanism design. And what they suggested as a template for thinking about these questions was the following. First, characterize the Bayesian optimal mechanism for every IID distribution. Okay, so understand it. And then consider the following distribution-independent benchmark. For if you are given a particular prior, there's a well-defined optimal truthful mechanism. It gets a certain revenue for that, for a particular bid vector. And set your profit benchmark, your target, to be the best any of these mechanisms could have done on that input. Okay? So this is a really strong benchmark, because you're sort of allowing, if you think of an adversary who's able to sort of get this kind of revenue, you're allowing the adversary to actually tailor the prior distribution, and hence the mechanism, to the particular bid vector you're working with, and potentially that results in a lot of revenue. And it's very unclear a priori that you could compete with such a benchmark. But they suggested, give it a shot. And they suggest, try to design a prior-free mechanism that approximates this benchmark on every input. And then the really great thing about this is it connects us to the economic results, and it allows us to say, if you can compete with this, that your auction is simultaneously competitive with all Bayesian auctions. And in fact, it's better than any Bayesian auction, because it's point-wise competitive with the best Bayesian auction for that input. Okay. So, and then they suggested that you get the best possible competitive ratio, which no one ever does. But, okay. So, and in retrospect, this was exactly what the digital goods results did. The Bayesian optimal mechanism for digital goods is just to charge the best price, which is the price that maximizes the price times the probability that the agent will accept the price, the probability that their value is above that price. That's the optimal mechanism for a particular F, for a particular prior F. And so what is the distribution-independent benchmark? It's just the best fixed price auction. And we know how to compete with that using random sampling type auctions, and it's all very nice. Okay. So I'm now going to kind of give a bit of a survey of kind of where we stand with this sort of program. And I will say that this is a very limited survey. I'm not mentioning a lot of papers that many of you have written that I should be mentioning, but I just want to give like just the high-level points here right now. So so for Bayesian optimal mechanism design, you know, we're good. This problem is solved in the single parameter setting. There's an intermediate framework that's been considered in some recent papers between knowing the prior model and the completely prior-free model. And this is when you assume the values are drawn from a distribution, a prior distribution, but the auctioneer doesn't know what that prior is. So in this setting, the goal is knowing, you know, you get told that the values are going to be drawn, let's say, for some regular IID distribution. And what you try to do is design an auction whose expected performance over values drawn from that distribution is within a constant factor of the best possible for that distribution. Okay, so this is a statement about averaging over all the inputs. And in fact, such results have been obtained. I think sort of some of the strongest results are in this paper by Dangwat, Natai, Roughgarden, and Yan, who were able to basically get constant factor, basically do this for matroids when the prior distribution is regular, and for downward closed settings when the prior distribution is MHR. Okay, so that's sort of that. And then I'm setting the target for prior free to design an auction that on all inputs is able to compete with this, this benchmark that I already discussed. Okay, so, oh, and I should say that essentially this has been done for any single parameter setting where the feasible sets are independent sets of a matroid. Okay, so the question that I was interested in is, you know, what about other set systems? Can you compete with this for other set systems? And what I'm going to talk about in this talk is a very, very simple setting. These are sort of preliminary results, arguably. And it's the following setting. It's sort of the simplest non-matroid setting you might imagine. You have two markets, each with n agents. And the feasible allocations are any subset that lies exclusively in one of the markets. Okay? So this might model government regulation where you're not allowed to sell in one of the markets or in both markets, or the fact that I can take my falafel truck only to one place, or whatever it might be. Okay, so the question is, can we design a prior free auction that gets a constant, that basically is competitive with this benchmark? And unfortunately, the answer is just no. And the first result is that for any truthful and expectation auction for this simple setting, there is going to be some input on which it can't get better than a log-n fraction of this revenue, even if I sort of relax the benchmark to only optimize over monotone hazard rate distributions. I'll say a few words about the proof, but first I have to quickly review Myerson. Because we have to understand what we're competing with, the benchmark. So as you probably all know, Myerson defines this notion of virtual values, which sort of shifts the values down by some function that depends on the prior. And then the optimal mechanism, at least for regular distributions, is to simply find the feasible set that maximizes the sum of virtual values. So instead of maximizing surplus, as in, let's say, VCG, you maximize virtual surplus. Okay? And then you have to do something else if the distribution is not regular, but I'm not going to get into that. And so the two standard kind of classes of priors. We've already heard about them. Most restrictive being MHR distributions, less restrictive being regular, have the property that these are monotone increasing with the values, and hence this is a monotone allocation rule. Okay, so let's quickly just see what happens with Myerson in the two-market setting. Okay, so again, what Myerson would do is compute a virtual value for each agent, which I'm going to call the virtual value for agent I, WI. And then it's going to look at, sort of ignore all the agents with negative virtual value. And from now on in the rest of the talk, I always ignore all agents with negative virtual value. I'm not going to keep saying that. So when I talk about virtual values, assume they're all non-negative. And then just allocate to the market where the sum of the virtual values is higher, okay, of the non-negative virtual values. And what are the payments? Well, since you can't possibly win if your virtual value is negative, as usual, the way we figure out what the payment is how much could you lower your bid and still win? Okay, what's the threshold bid? Well, you can't lower your bid to the point where your virtual value is negative. So you certainly can't, the threshold bid can't be less than the inverse virtual value of 0. Or the case where the auction actually makes more profit is the case where the sum of the virtual values in the two markets is actually very close to each other. If the sum of the virtual values in the two markets is close, then that agent can't lower his bid very much and still win. And basically, what is he going to pay? How much he can lower his bid is still win. So the key point here is that the case where you make a lot of money is exactly the case where the virtual surplus in the two markets is very close to each other. Okay, so the proof is actually not very difficult, although annoying, many technical details. But the idea then to show that you can't compete with this benchmark is to construct a distribution over bid vectors that have high surplus in both markets, and the expected surplus in both markets is equal. And these distributions, for those that are in the know, are kind of truncated equal revenue distributions. So we know that the expected revenue of any truthful mechanism on these distributions is constant. But then we can actually show that for any bid vector in the support of these distributions, we can actually find some MHR distribution such that the virtual values, these shifted values in the two markets, become equal. And therefore, each agent actually pays full surplus. And you can do this in such a way that basically for each vector in the distribution, you get to choose the prior distribution. You shift things to make them equal, and you essentially extract expected revenue of log n on a constant fraction of these bid vectors. And therefore, since the expected revenue, the ratio of the expected revenues is log n, there has to be some vector in there where the ratio is log n. Okay. Yeah?
Just to be clear, the valuation profile you construct here looks nothing like MHR.
That's right.
Like equal revenue.
It looks like equal revenue. That's right. So this benchmark is too strong, I will argue, because, we really would like auctions that we can, we'd like to be able to say we're very close to some very natural benchmark. And we saw many reasons why this benchmark was way too strong. In fact, even if I told you the prior and I allowed you to get this revenue on each bid profile, it would be much higher potentially than Myerson would be. So this benchmark is allowing the adversary to choose the placement of the values into the set system and the distribution that those values are postulated to come from pointwise. And then we're looking at the worst case. And this is just, impossible to deal with. So what we're going to do instead is symmetrize the benchmark in the following way. We're still going to allow the adversary to choose his favorite distribution that the values might come from, but those values will be placed randomly into the set system. So basically what happens is, what is this expectation here? For a particular prior distribution f, it's the expected value Myerson would get over all random permutations of those values within the set system. And then we allow this adversary to choose the best possible f, the best possible prior. And, okay, so we would like, and I guess the major point here is that an auction competitive with this benchmark is still simultaneously competitive with all Bayesian auctions. So we still have the nice economic corollary. In fact, we have it point-wise, because if the values are drawn IID from a distribution, then every permutation of the values is equally likely. So, I mean, it's again stronger than a statement about, averaging over values. Oops. Okay. And then the question is what happens in our context. And the claim is that in the exclusive two-market setting, once you use this benchmark, the benchmark actually becomes a constant times the best fixed price revenue. Okay? And notice again, this can be, a factor log n smaller than the sum of the values in the two markets, but it's still the case that Myerson can't get more than the best fixed price revenue in this setting. And it's easy to get a constant fraction of this revenue in this setting using ideas from digital goods auctions. So I'm going to try to show you the idea of the proof because it's sort of cute. And it's basically the proof boils down to getting an upper bound on this benchmark. So fix a set of values and fix any regular distribution, which preserves the order of the values. And what we need to do is bound the probability that the difference in virtual surplus between the two markets is small, because that was exactly the case where you were able to extract a lot from the agents. And we'll do this in a crude way. We'll just use the fact that unless the difference in virtual surplus is less than the virtual value of agent I, the payment from that agent can't be more than the inverse virtual value of 0. So if these are the sum of the virtual values in one market, this is the sum of the virtual values in the other market, if this is different, is bigger than agent I's virtual value, then no matter how low he lowers his bid, it's never going to, we're never going to consider it when it's below 0, that market will still win, okay? So the most he could lower his bid and still win is down to the inverse virtual value of 0. Okay? If the difference is, I meant if the difference in virtual surplus is more than WI, then the payment is at most that. That's what I meant. Yeah, you're right. This is supposed to be a more than. If the difference is big, then the payment is small.
So it's either going to be that or 0. So by at most, you mean that or 0.
That or 0, yeah. Okay, fine. Okay. So what we're going to show is that for any particular agent whose virtual value is Wj, the probability that the difference in virtual surplus between the markets is less than his value is like 1 over square root of j. And this will be enough to prove the theorem. It's just simple to show that this is enough to prove the theorem. So the proof is actually inspired by sort of the analysis of the influence of a player in weighted majority voting and acute proof due to Erdős, which I'm essentially going to show you Erdős's proof and not how we extend it, but it's just really cute. So do I have 5 minutes or not?
Yes.
Okay. Okay, so first of all, why is this like weighted influence of a player in weighted majority voting? Because imagine that you have a bunch of n players or n voters voting for one of two candidates, let's say equally likely. But the way we're choosing a candidate is by summing their weights, the weights of the votes for each candidate. So we have a problem with the payment being large exactly when player I can swing the election, meaning that the difference in the sum of the votes is small. Okay? So let's just see how you do this again, I'm going to do this in a special case where the N agents are placed equally likely into the two markets, and all the values below Wj are 0, okay, just to make this really simple. So we'll say a subset of the top J voters is bad if their weighted sum is more than the weighted sum of the rest, and they can swing the election in the sense that the difference in the sum of the weights is less than Wj, okay? This is the case where player J is sort of going to get paid a lot when this difference is less than Wj. And suppose T is another different bad subset. So the claim is that it can't be that S is a subset of T or T is a subset of S. Why is that? Because suppose the partition is I have S and I have the rest of the agents, and T is some superset of S. So that means I'm still bad if I move the remaining elements from T over to this side. But if S was bad, the difference in the sum of the weights between these two was less than or equal to Wj. Okay? Which means that when I move elements over, it has to be at least Wj. Okay? So I saw a couple nods, so that's good enough. So that means that this collection of bad subsets has to be an anti-chain in the partial order defined by inclusion, which we know contains at most J choose J over 2 elements, and therefore the probability of this bad event is small. Now I should say that this is completely ridiculous in our context, because in our context we were partitioning the agents into two equal-sized subsets. And so if all the Wi's were equal, the probability that the difference is equal to 0 is 1. But that's exactly the case where the sum of the values is equal to the fixed price revenue. And so basically you can deal with it. So let me end. So we showed that for one of the simplest non-matroid settings, no prior free auction can compete with this benchmark. But once we symmetrize, then we can get a competitive prior free truthful auction. So we have some ideas about the extensions, but it would be really nice to get some general prior free results, strong prior free results for all downward closed set systems. And I should say now how this connects to what Jason said earlier. So Jason's paper with Chichiyan shows that there's a prior free mechanism that for all downward closed set systems that's constant competitive to the optimal MV-free benchmark. Okay? But in the non-matroid setting, it's not actually known exactly how that relates to the optimal IC mechanism. Okay? So that's another way to approach this, is to think about that, again, the connection to NV-free, because then we already have the mechanism that they designed. But it's also a slightly different model in that they are assuming that the players are placed, that the auctioneer faces a random permutation. I'm okay to use that in the benchmark, but I'd prefer that the mechanism doesn't depend on that. Okay, so that kind of might change things. It's not really clear. Okay, non-downward closed settings is complicated. And multi-parameter settings is also complicated, but we might have some new prior free results with Tak and Jason and Nikhil Devanur on that topic, so stay tuned on that. But thank you.
Questions?
Yeah, I mean, I think that, well, we already know the work Jason spoke about relaxes, in some sense, this benchmark. It's not clear exactly how they relate to each other in this more general setting of downward closed. So, so I think, you know, I was really infatuated with Tim and Jason's original suggestion, and I really thought, oh, it would be so great if we could do that. It was just like totally awesome. But that, I think I agree that it's a little bit less clear right now. I mean, Jason argues envy-free. It's not really clear. So there's still more thinking to do, I think.
We can take one more question if there is any. Okay, thank you.